So we are going to be continuing our conversation using process controllers, and this time we're going to be tackling something called an integral controller. So this GC here is going to be related to an integral controller this time, not a proportional only controller. So what ends up happening is first we can define the G for our process, and for this problem setup, we're going to say this is a third order process. So that is our process gain over our tau s plus 1 cubed. So here is the transfer function for our process. Now, for our controller, usually we would make the assumption that this controller has just a value of kc and we would move on. However, in this case, what ends up happening is that we incorporate this term 1 over this tau I s plus 1, or I believe it's just tau is. And this tau I is the reset time for our integral controller. So it is actually different from this t, which is our time delay for our process. So in order to determine our open loop transfer function, so let's say our G open loop, we are looking at everything that follows the forward direction of our process. So this process back here goes in this reverse order back to our comparator. So this open loop looks something like our GC times our GP. Now finally, our last little derivation that we're going to do here before we move on to some code, we want to derive the overall transfer function for our closed loop. Now if you remember, there is an easy way to determine this, and that's basically saying, well, we want all of these functions in the forward direction. So that is actually just our open loop transfer function, GC, GP. Or rather, not. In this case, our open loop and our transfer functions in the forward direction are the same because we don't have that measurement device. So this is just transfer functions in the forward direction, and that's over 1 plus transfer functions in the open loop. So if we had GM here, the GM would show up in the bottom. But for right now, that's just going to be GC times GP. So this is now our closed loop transfer function. And what I have done is I've actually already coded this in. So you see here is the G for our controller is that 1 plus 1 over tau is. So tau I is that reset time that we talked about. We have the G for the process. So that's our process gain times our tau, which is our dead time, s plus 1 to the third for a third order transfer function. And then just what we had derived is that G for the closed loop. So if I go ahead and run this right now, we see that we get this frequency response graph that we have actually done the same thing right here. This is all just copy and pasted from above. And we see that if we look at our crossover frequency, like we had done last time, so that crossover frequency looks like maybe like 1.8, let's say. If we go ahead and find that point on the graph, we see that we get a amplitude ratio of 0.11. And so this tells us that when we run our process, it's going to remain stable. So this is just the Wikipedia page, although Ziegler-Nichols method. And basically what happens is that we have our proportional gain, the Kp. It is increased from 0 until we reach something called the ultimate gain, which is the Ku. At which point we also determine the oscillation period, Tu. And for our integral controller, so this is our proportional integral controller here, we find that the K for our process is 0.45 times Ku, which is the ultimate gain again. And our tau I, that reset time for our integral controller, is 0.83 times the ultimate time, or the oscillation period, rather. So this is pretty easy to find because it just involves us cranking up our KC, so that's our controller gain. We just crank this until we find that our system is somewhat stable. So let's say, what happens when we make this 10? Pretty unstable. We don't want that. Maybe we need to go lower, something like 9. Still goes unstable. 8. Okay, well that doesn't look too bad. So if we find our crossover frequency, about 1.82, yeah, we see that our estimate is around 0.89, so that falls just about under 1. We can probably use that as our ultimate gain. So now what ends up happening is, in order to get this to that kind of that critical value for which the process remains stable, we have to take this rule, so 0.45 times Ku. So if we go and do that, so 0.45 times that, so this will give us, or sorry, we want to keep, oh no, okay, never mind. So let's say, all right, so I did bung something up a little bit. Our tau had to be set to 2, and that's actually what we did before 2, and that didn't carry over. So this tau is now set to 2, so our time constant should be correct. And I just reran everything here. And so this is, I guess, a good chance to just go through this one more time for practice. So I'm going to zoom in here. First off, we found that ultimate K, so times 0.45. And this is the Ku times the tuning times Zn parameter. And then to find that tau I, it's 0.83 times the time period between a full oscillation, so between two peaks. So this peak is at 18.7. Minus what we have here is 11.5. So this is times 0.83. So now this is our TU times the Zn parameter. Okay. Now if we run this with the new values, we see that very similarly, we run this to a steady state, and this is representative of the previous setup before we did any messing around with using the Ziegler-Nichols method. We find that our crossover frequency is at about 0.87, and if we try and find that on our graph, 0.87 gives us an amplitude ratio of 0.99, which is very, very close to 1. So we were correct in that assumption that this is kind of that critical K value, that ultimate K value. But now if we run this, we see that we get kind of a different graph. Now if we look at our crossover frequency, get something about 0.72, and 0.72 on this graph gives us an amplitude ratio of about 0.68. So now that we have that K value all figured out, now we want to look at the oscillation time. So what I'm going to do is I'm going to choose two peaks. These two look pretty good. And find my time difference between them. So this one's at about 5.7 seconds. And this one's at about 9.4 seconds. So we get, let me just do it this way. So this was what? 9.4 minus 5.7. 5.7. This should give us the time between one full oscillation, the time between two peaks. And that value gets multiplied by 0.83. And now if we go ahead and we run this simulation, we find that our frequency response diagram shows that we do indeed reach a stable state, a steady state. And if we go ahead and run this Boré frequency analysis, find that crossover frequency about 1.51. So if we do go to about 1.51, we see that our that amplitude ratio is about 0.61. So that's how we get these tuning parameters using the Ziegler-Nichols method.